Mr. Leonard, we are very happy to have you, and begin at your discretion.
Thank you. Let me start the program here. Can everybody see that still? I'm just going to do one thing. I'm going to switch to display. Everybody seeing that okay?
Your PowerPoint is up, sir.
Okay, fantastic. Yeah, thank you for inviting me. I think it was an invitation sent out some months ago, and I do apologize for the technical glitches. Part of that is because I didn't routinely check my settings. As you can see behind me, this is not my home. I am actually at our Schmidt telescope on Mount Bigelow, just north of Tucson. I had to observe tonight. There was sort of a scheduling issue. So I'm up here tonight, but no need to worry. I am not validating asteroids behind me, potentially dangerous near-Earth asteroids. I've got a colleague on a remote desktop that's taking over for the next 2 hours or so. So rest assured, asteroids are being looked for as we speak here tonight. Thanks, everybody. My name is Greg Leonard. I am an astronomer with the Catalina Sky Survey, and we are a NASA-funded project, and our sole mission is dedicated to discovering and tracking near-Earth asteroids. We're based here at the University of Arizona, and I've been with this project for about 6 years now. And in the past, I've worked part-time or full-time in one way, shape, or form in planetary sciences since the early 90s. And I'll talk a little bit about that later too. But for tonight, just a few topics. I'll just talk briefly about, what are asteroids and near-Earth asteroids, particularly their, I guess, well-known reputation, their deleterious effects should they impact our planet. And then I'll describe how we discover near-Earth asteroids here. And I'll also talk about the flip side of near-Earth asteroids, and that's some of the benefits that they offer Earth. And then finally, I'll finish up with some interesting incoming attractions. By the way, I'm not sure how many folks are on this tonight, but if you want to reserve questions till the end, or if people want to put questions in the chat, then Raj, maybe you can moderate and chime in if somebody has a burning question as I scroll through the slides and deliver the presentation.
I can do that, Mr. Leonard. And for the record, we have 26 people attending.
Great.
And that includes you, of course.
Yeah.
So 25 plus you.
Yeah. So just, briefly, as many of you know, asteroids are, quite simply put, the leftover building blocks of our solar system's formation. And there's really no lower limit to what an asteroid is, but, we sort of take 1 meter to be the lower limit. And these things can be very large, up to many, many hundreds of miles across. They can be solid bodies, being pure solid iron, nickel, cobalt. And it can also be rubble piles, which you see clearly here with the near-Earth asteroid Bennu, which was just visited by the OSIRIS-REx project, and a sample collected and gathered, which is en route back to Earth. We're excited to see samples returned, and in the University of Arizona labs in particular. But you can see it's really low density rubble pile, the surface here. And I think John Lewis probably said it best, that the compositions of asteroids are extremely diverse. They range from lake bottom mud to very organic carbonaceous chondrites, all the way up to like high grade stainless steel with iron nickel asteroids. Most asteroids, as you know, reside in the main belt. The total mass of all the main belt asteroids is still only about 5% of the moon's mass. And all these green dots here circling between Mars and Jupiter represent main belt asteroids. The little white flashes that you see on this animation represent actually the time of discovery. And you might notice, I don't know if you can see my cursor here, but right down in here, can you see my cursor, by the way?
Yes.
Yes.
Thank you. Yeah, right down in here, you see sort of a gap, and that represents the monsoon, the summer monsoon months in Arizona, when we're often not observing because of lightning and cloud cover. So there's a little bit of gap in the summer months. So near-Earth asteroids, simply put, are asteroids with orbits that can bring them in close proximity to Earth. A little more technically, it's any asteroid that has a perihelia that is less than 1.3 astronomical units. And that's represented by this, this is two-dimension, but you can imagine sort of a spherical shell, that's 0.3 AUs out from the Earth. So any asteroid whose orbit brings it within that sphere is technically a near-Earth asteroid. There are a few families of near-Earth asteroids. The Apollos spend most of their time outside of Earth's orbit, and then they kind of cruise across Earth's orbit. Ottens, by contrast, spend most of their orbital period inside the orbit of Earth, and they just peek out here. Amors don't cross Earth's orbit at all. However, they're close enough where they can be gravitationally perturbed to eventually become Earth-crossing asteroids. And then finally, there's a little sneaky group here called the Asteroids, and they have orbits that are exclusively within the orbit of Earth. And as you can imagine, these are very difficult asteroids to observe only on the edges of the day and twilight when we can pick these up. I think there's only about 34, 35 known Asteroids. And recently there was an object discovered by the Zwicky transient factory in Palomar that was actually within the orbit of Venus. So they called it a Vatira as opposed to an Atira. Here's just a little fun animation. It's just a little bit outdated, but it's going to show in sort of 10-year chunks from 1999 to 2009 and 2018, sort of the discovery rate of near-Earth asteroids, which you can see is exponential. Here's 1999, all the near-Earth asteroids known. Quickly, we zoom in here to 2009, and then here's 2018 that's going to pop up. There's currently over, we're approaching about 27,000 near-Earth asteroids. And there's the main belt asteroids in orange color. Obviously, these asteroids are not the scale, otherwise we wouldn't be able to see them whatsoever. So there are essentially three fates that await any near-Earth asteroid. They can be flung into the sun, they can be ejected from the solar system, and in fact, about 20 or 30% of them will collide with Earth. So out of the 27,000 or so known near-Earth asteroids, about a third of those could collide with Earth. Now, we're talking about collisions of very small bodies too, the 1 meter and a few meters across, which are inconsequential. And we're also talking about, deep time. So this is spread out over millions and billions of years. Interestingly, the lifetime of near-Earth asteroids is only a few million years, maybe upwards to about 30 million years. So when a lot of folks hear this, they say, okay, if near-Earth asteroids only survive for a few million years and the solar system is 4.5 billion years, why aren't they all gone? Well, there's a mechanism by which the population of near-Earth asteroids is slowly but continuously populated. And that happens as a result of a few effects, which I'll explain here. Again, here's the main belt asteroids, and we're just going to zoom in on a random asteroid here. And many of you have heard of the Yarkovsky effect. So, the sun is heating one side of the asteroid as it's rotating. That thermal energy is re-radiated, but the object is spinning, so it's re-radiated, giving that asteroid a slight impulse, just the tiniest minuscule rocket thrust in one particular direction. So when this happens, the asteroid begins to slowly migrate. This is over many, many millions of years. Eventually, an asteroid will wander into one of the Kirkwood gaps, which are the resonant gaps that Jupiter sweeps out. So the objects wander into a Kirkwood gap. It's picked up by Jupiter in one of these resonances and then slowly steered into an Earth crossing orbit. And here they are. You know, typically an object might first be steered into a Mars crossing orbit, and then that's further perturbed with, you know, the semi-major axis enlarging and eccentricity, and then it becomes an Earth crossing asteroid. Well, let's talk about some of the effects. Probably the last best known impacting asteroid occurred in southern Russia in 2013, and that was over the small city of Chelyabinsk. And this is a 20-meter object that came out of the direction of the sun early in the morning. And you can get on YouTube and see videos all day long. And I'm going to show you just one of them in a moment. But this object came in from the direction of the sun at a very shallow angle, and it mostly detonated in the upper atmosphere, you know, about 15, 20 miles up, and all of its energy was released to the atmosphere, but the shock wave made it down to the city. And I'm going to show you this video here in just a moment. There were many fragments from the asteroid that just harmlessly free fell to Earth. And I have a little piece of that. They're kind of readily available if you go to some rock and gem shows. There were about 1,500 people that were injured. Nobody was killed, fortunately, but there were a lot of lacerations from glass that was imploded and broken, and some bruises and maybe some broken bones too. Yeah, and by the way, the impact had the force of roughly 15 to 30 atomic bombs, Hiroshima atomic bombs. So quite a bit of energy for what we consider a pretty small asteroid. And we'll get into talking about that in just a moment. So here's a video of the shock wave taken from some cameras, closed circuit cameras across the city. And well, you'll see the results.
Думаешь, может, спутник там уже же падал, а не
Here the camera saturates, then it kind of recalibrates itself. And then the shock wave hits. So you get the idea. Again, a reminder, this is a, just a 20-meter asteroid, the size of a school bus or so. And it created quite a bit of havoc that morning. Interestingly, NASA was conducting, looking at another asteroid flyby that very same day. And, maybe slightly embarrassingly, this asteroid sort of came out of nowhere and stole the show. Perhaps being from Arizona, this is probably, the best known asteroid, evidence of an asteroid impact, a meteor crater. And about 50,000 years ago, an object that was only 50 meters across slammed into the Colorado Plateau, with the force of the largest nuclear bomb ever tested by the United States, the Castle Bravo bomb on Bikini Atoll, a 10 megaton impact. Now, fortunately, no people were living there, but there may have been some woolly mammoths and ground sloths that were affected. This was, despite the relatively small size of the object, it left quite the impact scar, partly because, as many of you know, this was an iron nickel meteorite, and we're still finding, many meteorites scattered around the plateau to this day. And of course, this is the crater that Gene Shoemaker studied in the late 50s and did his PhD thesis on, and conclusively proved that this feature, this phenomenon, was actually an impact. And many folks previous to that believed it was a volcanic structure, a cryptic volcanic structure, as they called them. But, through looking at the overturned beds at the rim, the high temperature and high pressure pseudomorphs of quartz that were found there, these were minerals that were previously never known to exist. It was the smoking gun for this being the result of an asteroid impact. And I guess the granddaddy of them all, this is the Cretaceous Paleogene impact that wiped out the dinosaurs 66 million years ago. And this was, 6 miles across, had the energy yield of 5 billion, with a B, billion megatons of TNT. And that is 100 million times the largest bomb ever detonated on the planet, which was the Tsar Bomba. The Soviets detonated that in the 50s. So this was a big one. You can see in the lower right, this is the geophysical signature of the impact. And this is really how it was first detected by an oil exploration company in the Gulf of Mexico, but was later identified by planetary scientists as a feature of interest, further investigated. And to this day, they're still drilling projects, down into the sea bottom and into the rim and the central peak to better understand, what occurred there. But we know that not only the dinosaurs, but 75% of plant and animal life on the planet was extinguished in a hurry. And we're probably here as a result of that, because it left an ecological and environmental niche for the mammals, including us, to eventually evolve and dominate the planet.
We have a question from the audience asking, was the Tunguska event of 1908, was that something similar to Chelyabinsk, an asteroid that just never hit the ground?
Yeah, that's sort of the current thinking, is that a lot of folks postulated over many decades about, was it a comet, because there was never any fragments discovered, like metallic or chondritic. So maybe it was a comet. Even people postulating that was a small piece of antimatter that passed into the Earth. I believe the current thinking it was an asteroid that just completely, vaporized in the atmosphere, and the shockwave did the damage of pulverizing, 2,000 square kilometers, 800 square miles of, Siberian tundra and forest. So yeah, that's the current thinking. It was an asteroid, but I still believe there's a lot of folks, wanting to study that further.
And one more question from the audience is that Chelyabinsk, you were talking about the classes of NEAs. What class was that, if that can be known?
Yeah, frankly, I don't know the answer to that. However, there was a documentary that I saw a couple of years ago that traced back the trajectory of the object. And frankly, I don't recall if it was tracked to any specific one of those families. Now I'm interested to go back and see if it was indeed, an Aten, which could very well be the case coming out of the direction of the sun, but it doesn't necessarily need to be an Aten. It could be an Apollo that, slipped around the sun and then, hit us from the sunward side as it was heading back out. Good question, to be determined. So, in talking about the threat of near-Earth asteroids, the threat is in part proportional to the size of the object, because the kinetic energy is equal to the mass, which is related to its size, roughly, and of course the velocity squared. But let's just talk about the size of the object. And at the bottom axis, you see diameters going from simply 1 meter objects all the way up to objects that are greater than 10,000 meters or 10 kilometers across. Not surprisingly, there are billions of 1 meter objects out there, and there are far less of the larger objects. And one analogy I think of is if you drop a glass of water on your kitchen floor, you go to pick up the fragments, there's a couple of big fragments, there's more medium-sized fragments, and if you were to take a hand lens or a microscope to the floor, you'd probably find thousands and thousands of little microscopic shards. And that's sort of what the distribution of asteroids are as well, main belt asteroids and also near-Earth asteroids. So there's an inverse relation between the diameter of the object and the size of the population. Now here's sort of a look at the percentage discovered of those populations. Not surprisingly, we discovered 99, maybe 100% of all objects that are 10 kilometers or larger across. And that's not surprising because these are large objects. They're reflecting a lot of light from the sun, so we're easily able to detect them. The same is true for the 1 kilometer objects. We've got about 95% of those discovered. There's roughly 950 of those. There's probably a few of these monsters lurking out there, but every year, every couple of years, we discover one more, and we're bringing that population close to 100%. Again, not surprisingly, the little tiny asteroids were way less than 1%, but these are largely inconsequential should they impact the planet. And this is sort of the sweet spot in here, is these 100-meter and a few 100-meter asteroids where we've only discovered about 20%, a little bit higher percentage as we move toward the kilometer range. But this is sort of the population that we're currently, really interested in discovering. A slightly different diagram. Again, we've got the diameter here on the x-axis going from 1 meter objects all the way up to greater than 10 kilometers. And on the y-axis now we have the impact frequency. And again, not surprisingly, the small objects tend to impact with higher frequency because there's just more of them. The 1 meter objects are really impacting a couple to even a few per month. Now, if you were to see a 1 meter object impacting over your town or city, it would produce quite a show. It'd be this beautiful bolide. However, most of the planet is remote, covered with ocean or otherwise remote landscape. And so these are largely go undetected by humans. You get into, sort of these mid-size here, and objects that are about 100 meters across, roughly every 1,000 years, something hits. And as you get into a few 100 meters across, then you start getting into tens of thousands to hundreds of thousands of years. So what are the results there? Qualitatively, we'll start at the bottom here. This 1 meter object, again, is what I call sort of a party stopping fireball, right? You're barbecuing in the backyard, you see something like this come in and everybody just drops what they're doing and marvels at it. And then at the top end of the scale, this is your Cretaceous Paleogene impactor here. This is, several miles across. That is a planet destroyer, folks. This is going to wreak havoc. Firestorms across the planet, tsunamis that are many miles high, the acidification of precipitation in the atmosphere, nuclear winter, the list goes on and on of the effects that result from an impact of this size. Something that is about 1 kilometer across that's not necessarily a planet destroyer, but it's certainly a planet disruptor. Even if it hits in New Zealand, we're going to have the effects of, again, nuclear winters and firestorms and tsunamis across various parts of the planet. And it's not something that I think, even on the other side of the planet, that we'll be able to shake off in a year. It's probably going to be decades or centuries of effect. So once again here, let's take a look here. So obviously we're really concerned about these big ones, but recall that we've got all these ones dialed in. We're almost 100% of this population. Down here, these are largely inconsequential. They'll mostly burn up in the atmosphere. So it's really this sweet spot right in here, the 100 meter to a few hundred meters across, upwards to a kilometer. But again, we discovered 95% of these. So this is sort of the sweet spot. And this is sort of the, it's been a congressional mandate now since 2008 to discover 90% or more of the 140 meter or larger diameter asteroids. And the last graphic I showed, we're about 20–25% there. So, we have a long way to go. That said, Chelyabinsk was sort of down in here, right? And we saw the damage that did. So I believe our calculus is sort of shifting. Once we discover all these 100 meter or large objects, we might want to start, of course, increasing our ability to detect smaller ones that aren't planet killers, but, they can be a city disruptor. Yeah, one disclaimer, I guess I have to have somewhere in the talk, is that currently there's no known near-Earth asteroid that is on an Earth impacting trajectory. There are virtual impactors. There are objects that we've discovered that have impact solutions, but about 99.9999 forever percent of the time, with further follow-up observations, those impact solutions go to zero. So right now we're okay, but I'm up here on this mountaintop for a reason, because there always is the chance of impact, be it next week or in 10 million years from now. So what do we do? Our project is not, we're not tasked to decide how we take objects. That is other NASA funded projects, and also European Space Agency projects, Japanese Space Agency. And there are smart folks out there that are thinking about what we call asteroid deflection. What happens when we find one? Not surprisingly, it's not a one-size-fits-all, because it depends on how large it is. Is it going to hit next week, or is it going to be in 59 years or 200 years into the future? What is it composed of? What is its density? There are just so many factors that come into play when we have to design a mission to deflect asteroids. But probably the most simple one is a kinetic impactor. That's just slamming something into it and trying to nudge it away a little bit. If that's done further enough ahead of time, just a little tiny nudge, many years in advance, can be enough to have the asteroid miss us down the road. Same thing would be for a blast deflection, the same idea. You're not impacting it directly, but a blast. A cool idea, swarm of bees, or simply laser ablation that's heating up a portion of the asteroid, and volatile material would boil away, providing a little bit of thrust to move the asteroid out of harm's way. Oh, by the way, we have a mission in progress, NASA's DART mission. This is the dual asteroid rendezvous targeting, or something like that. But it was supposed to launch in July, but now the launch date is pushed back somewhere between November and February, depending, I guess, on when the best time of the launch window is. But this is a binary system, Didymos and Didymos B. So they're going to slam a kinetic impactor into this little guy here that's, about 1.5 times the size of a football field. And they're just going to see how it changes the orbital period. So, we're discovering asteroids. We're dipping our toes into, deflecting asteroids and learning about that. So, we are lucky to live in a time where we're doing all these things. People say, are we doing enough? I'd say, yeah, proportional to the threat, that near-Earth asteroids pose, we are actually doing, I think, the right steps at the moment.
Quick question from the audience. Is there an average or median speed at which these NEAs move? Yeah,
that's about 19 kilometers per second. Okay. So you're looking at about 12 miles per second. That is an average. They can be a lot slower. The slowest they can be is about 12 kilometers a second, which is maybe 7 or 8 miles per second. And the fastest they can be, well, if it's a comet coming in, say from the Oort cloud. Now I know I'm talking about comets, but a comet can have sort of cosmic velocity of 70 kilometers a second. Asteroids are typically highest would be, I think, in the 40 to 50 kilometers a second. And that's a great question because, as I mentioned earlier, the kinetic energy yield is proportional to the mass of the object and the velocity squared. So yeah, mass is one thing, but velocity squared is really where the damage comes in. So yes, it does make a difference how quickly these things are moving.
And for the record, 12 kilometers per second is just over 43,000 miles an hour.
Yeah, it's cooking. Yeah. We don't have much reference for that on the planet here.
And also, just check from the chat room, does the Catalina survey, does it take 30-second or 60-second snapshots of the sky?
30-second integrations, yeah.
Thank you.
Yeah. So we talked about the Yarkovsky effect earlier, and one idea is to spray paint an asteroid or wrap it in tinfoil. So basically it mutes or enhances the Yarkovsky effect to have the asteroid move out of harm's way. And of course, an elegant solution, maybe with enough time, is a gravity tractor, just sort of let gravity do its thing and nudge out of the way. And when all else fails, we got Bruce Willis at the ready, I hope, to send up and take care of asteroids. Okay, well, that was a great question because it's going to segue into how we discover and track near-Earth asteroids here at the Catalina Sky Survey. So this is where I'm sitting right now. This is Tucson City down here, and this is the Santa Catalina Mountains. This is the summit, 9,152 feet, and I'm 1,000 feet lower than the summit on Mount Bigelow. And we've got a couple telescopes we use here and a couple telescopes we use up here. We're actually beginning to get time on the 90-inch telescope on Kitt Peak to also do some surveying. But these are our primary locations here next to the city. Surprisingly, yeah, if I go out the door here, just to my left and I look out, I can see the city lights, but I'll tell you what, we still get really good skies here and it's plenty dark enough to do the work that we do. This is the suite of instruments that we use here in the Catalinas, and we've got 2 survey or discovery telescopes. I'm sitting at this one right here, right now. And then we've got 2 follow-up telescopes that are used for tracking the objects after we discover them. And all these are reflectors, largely prime focus instruments. This one is a Cassegrain design. Interestingly, the telescope, the 1 meter telescope over here to the far right, we are in the process of converting that into a prime focus telescope. It's going to give us a little bit wider field. It's going to be a little bit faster. It's going to be f2.5, maybe even faster. And the commissioning is going on as we speak. We're doing some collimations, so we're really excited to get that upgrade completed. The name of the game for asteroid surveying is sky coverage. It always has been. Unlike a lot of astronomers who might look at quasars and binary systems and whatnot, looking at tiny postage stamps in the sky, we cast a really wide net. And the telescope I'm at right now, the Schmidt, has almost a 20 square degree field of view. That's just a mammoth, field of view, and that enables us to cover all of the available sky in a lunation, which our lunations are 27 days. We only stop observing for a couple nights on each side of the full moon. So we can cover all the available sky with the Schmidt about 3.5 times, of course, contingent upon no clouds. The prime focus reflector, our 1.5 meter at the summit, is still a huge field covering 5 square degrees, and we cover all of the available sky to us 1.5 times per lunar cycle.
Is there anyone doing this kind of work in the Southern Hemisphere?
No, not so much. We used to have Siding Spring in Australia had a telescope that was aligned with our project, the Catalina Sky Survey, but they they could get funding to keep going. That said, there is the LSST, or the Vera Rubin telescope, that is in the process of being built in the mountaintops of Chile in the Atacama Desert. And that is a gargantuan telescope. You can see our camera down here. This is a monolithic CCD. It's a back illuminated CCD. It's 111 megapixels. It's probably one of the largest, monolithic CCD chips on the planet, not knowing what the Department of Defense has at their hands. The LSST project in Chile is going to be something like 40 gigabyte camera. It's just huge. It's not a single chip, but it's going to be a mosaic of chips. And so that telescope is going to more or less leapfrog over the capabilities that we have here at Catalina and the Pan-STARRS project in Hawaii, which is sort of our sister project out there. And that's going to come online. It's always 2 years off, but it seems likely that, maybe in a couple of years, that'll be fully commissioned and starting operations down there. So we'll have Southern Hemisphere coverage. And we're also, University of Arizona now has a NEO Surveyor project, and that's a space-based telescope system that has just received further funding, hopefully to launch later this decade and maybe get operational in 2030 or early 2030s. And that's also going to kind of leapfrog. That's an infrared camera that sits between the Earth and the sun, with its back toward the sun, and it's really going to extend our ability to look sort of in the daytime sky. It's going to look peripherally, outwards to the Earth and into space. So those two projects are really going to, revolutionize the cadence at which we can discover near-Earth asteroids. And we'll quickly get to the 90% of the 140 meter or larger objects with those projects, as they come online. Just a little eye candy, I guess, of the 1.5 meter telescope. This is the world champion telescope for near-Earth asteroids. Since, about 2005, it's discovered more near-Earth asteroids than any other telescope on the planet. It's currently working right now as we speak. This is the prime focus camera, this missile-looking thing up top here. And here's the 1.5 meter or 60-inch mirror sitting down there. Some corrective optics here that feed into, where the sensor is. There's about 7 lenses that sit in the base of this housing right here. And here's where I am right now. This is the Schmidt camera, and you can see, these are camera, not naked eye images, but you can still see the beautiful skies that we have, even adjacent to Tucson. And we get snow up here. Yeah, we're at 9,000 feet, so we're entering the fall and winter months, and we can get tons of snow up here, beginning, another few weeks, the snows might begin. So you can see behind me, I got this sort of 6 screens, and this is sort of what it looks like up close. And this is kind of how we monitor all the important things as we're, surveying through the night. We got weather, and we've got what the telescope is doing. This center upper screen here is showing our survey plan for the evening. And this is down here where we do the validation. And this is where we actually, do the work of visually looking to validate whether something is a real object or not a real object. In fact, the next slide, we're going to zoom into this coverage tool here, and I'll talk a little bit about the cadence and our survey program. So here we are zoomed in. This dark red here, and then you see it going down to the kind of lighter oranges here. This shows, for example, what the previous night's coverage was, and the lighter orange shows maybe the coverage of 2 nights ago. And all these rainbow colors going across this center strip show the nightly program. You can see beginning here, set 1 off in the western part of the sky, and this is west over here, and we move eastward through the night. And each of these sets here has about 11 or 12 fields that we observe. For example, we'll start observing in one field. We'll take a 30-second integration. Then it'll move over to the next field, 30-second integration, and it keeps moving through all the fields in the set. When it's done the final field in the set, it goes back to the first one and takes another one. So we collect 4 images of the same field in the sky, each image separated by about, roughly 5 or 6 minutes or so. You can see the Milky Way here. We largely stay away from the Milky Way. The moving object detection software, struggles with really dense star fields, and it's kind of difficult. There is new and improved software coming on board that may allow us to more freely just scan right across the Milky Way and hopefully discover lots of near-Earth asteroids that we otherwise would have to wait for until they emerge. And here's our lunar exclusion zone right here. The solid red line is the current situation for the moon, and we just don't want to go inside there, it's just too bright. And the dashed line represents the next night's lunar position. And so we might not want to, for example, surveying here, knowing that tomorrow night we might not be able to get a sufficient image quality to do a follow-up observation. Here's a little bit more how the sausage is made. We're collecting the 4 images. They're piped into this bank of computers, and a whole bunch of things happen there. Image calibrations, we do a star field fit. It goes through the moving object detection software, and that software identifies all known asteroids, be them main belt asteroids or near-Earth asteroids that are known. It looks into those catalogs and calls them out. And it also, of course, identifies new asteroid candidates. And it's up to us observers. We've got about 7 observers here at Catalina Sky Survey to blink through those 4 images to see if we see any objects that appear to be tracking against the background of the stationary stars. And interestingly, although the software is really a tour de force in its ability to pick out these objects, it really still takes our human cognition. I can make a decision in literally a split second on whether an object is real or not and move on, because we're really digging into the noise of the image. And right now the computers are not able to do that. The computers would be probably sending in lots of false positives to the minor planet center. Those false positives would require follow-up to get more positions for the object. But if it's not real, it's a lot of wasted telescope time. So fortunately for me, I love being an observer. It takes humans up here to do the work. And all objects, as I mentioned, are submitted to the Minor Planet Center at Harvard. That is the clearinghouse for all new astrometry, for new objects, for follow-up observations, and anybody on the planet that's involved in this business sends stuff in there automatically. And the Minor Planet Center will do a deep dive. This is all, of course, automated, to look in their catalogs. And if nothing matches the position or the motion, the direction and the speed of the object, then it's considered a new near-Earth asteroid candidate.
Quick question from the audience is that assuming an NEA, say 15 meters in diameter, how close does it have to get to Earth in order for you to detect it?
Yeah, good question. A lot of that's kind of circumstantial, but we discover lots of things that are pretty tiny, sometimes only a couple to a few meters across, including some objects that have impacted Earth. We are the first project to discover an impacting asteroid. That's 2008 TC3. And that object was only 1 or 2 meters across. And it was discovered, a couple million miles out, several Earth, or actually many Earth-Moon distances out there. So a pretty small object discovered, a couple million miles out, it's very impressive. So something that's 15 meters could be, many, many more millions of miles out there. It's a good question. In fact, I woke up, in my sleep thinking about that question more deeply today. And I want to start kind of evaluating the data set to see exactly where we are discovering the objects, how far from Earth are we actually finding things, so I can kind of better, more quantitatively answer that question. And
another question is, what kind of computers are used in this work? Are they supercomputers?
No, these are
linked together PCs.
These are just, you can kind of see in the image here, these are just kind of Dell, stacked computers here. They're nothing too fancy, a bit above sort of a home office desktop, but certainly not a supercomputer. We don't need, surprisingly, as much sort of computing oomph as you might think. And that's really a testament to the fast processing power, that is sort of at our fingertips, at improved rates year after year, Moore's law and all that stuff. So we need good computers, but not supercomputers. So this is a really standard image. You know, I click on a field, and that field might have 22 or more candidates for me to click through. Most of those are going to be false positives. They're going to be background stars, reflections, noise in the chip, cosmic rays, or any combinations of those things produce, you know, false positives. In fact, I will click through hundreds of false positives in the night, really thousands. And it's probably on average about 500 to 700 false positives for every one real near-Earth asteroid. So, you know, we go through a lot of false positives. Now, here's an image that actually has an object moving through it. Some of you may have already identified it. And this is sort of, I'll show you where it is if you haven't seen it yet. So this is a very typical presentation of a near-Earth asteroid discovery. In this case, the object it's a little bit streaked. A lot of objects we find that have an apparent slower sky velocity are more point-like. But this one is streaked. And again, you remember, we're sitting on that field for 30 seconds. So in 30 seconds, you know, the reflection from that asteroid burned across the pixels, and it's producing a streak. And that at least lets me know, in a qualitative sense, that this object is in relative near-Earth space. No, it's not necessarily an impactor, or it's not, you know, between here and the moon, but maybe it's you know, several million miles out or 10 million miles out. So it's a relatively close space. But this object, as typical as it is, you know, last night I got an object that looked exactly like this. This was actually an atypical object, because this was 2018 LA, which was the third impacting object ever detected before impact. And it was discovered by Richard Kowalski. That guy, he's worked for our project, you know, for about 17 years now. He's discovered the first, the second, and the third impacting objects. So he's got sort of, we call him the impact king, and he just keeps finding those things. This one landed in Botswana. And they actually picked up fragments of that one. This is actually, here's Richard Kowalski, and this is actually a fragment that he received of the very first object, 2008 TC3, that he discovered. This is discovered about 19 hours before it impacted. It was an object that was just a few meters across. And again, they found some fragments of the object. So it's pretty cool. The third object, well, it was the second chronologically, but the one that I didn't mention yet is 2014 AA. It was the very first near-Earth asteroid detected on New Year's night of 2014. Richard detected that one, and that one plunked down somewhere, I think, in the Atlantic Ocean. And that one was probably, you know, also like just a couple meters across.
Another question from the audience.
Right.
It's all strictly using light. There's no use of radar, infrared, any other wavelength.
Yeah, that's correct. This is all visual. We don't use any of those things. However, when we discover interesting near-Earth asteroids, other facilities, for example, the former Arecibo radar facility, you know, would ping microwaves off of interesting near-Earth asteroids to better understand their size and position and get an idea of what their composition might be. And infrared telescopes are used to do that as well. But we don't have any of those sensors, unfortunately. So we don't do any what we call characterization studies of the objects. We're strictly discovery and tracking. Here's a couple of plots updated the last couple of days. And this shows since 1980, the discovery rate of near-Earth asteroid. And here's the 1 kilometer objects down here in red, and the cumulative discoveries here. So we're, you know, we're upwards to 27,000 or so. And this shows discoveries as a function of project. And in green is the Catalina Sky Survey. We really started to up our game in 2005 when we moved to CCDs. It was mostly film-based back in here. And then we have, again, our sister project, the Pan-STARRS project in Hawaii. And they came on, you know, 7 years ago, and they're also quite capable. So we sort of compete as frenemies each year to see who can discover the most near-Earth asteroids. We're discovering, though, well over 2,000 new ones each year. And as you can see, it's just been an exponential increase of discovery rates. We have discovered, Catalina Sky Survey discovered almost half of all near-Earth asteroids. So we're pretty good at what we do.
Okay. The audience has again chipped in. Has Starlink or other similar type satellites, have they been causing problems with your operations?
Fortunately, not for us. Those constellations are typically in lower orbits, which is fortunate because those objects are only seen then sort of on the edges of the day in twilight, and they go into shadow sort of after twilight, so they don't really affect us. Not only that, but we do discover a lot of artificial satellites. Every night we're seeing artificial satellites. Some of them are identified in the catalogs, we know what they are, others are not. But objects that are going by in low Earth orbit, they streak so much that maybe one out of the 4 images that we're taking in a field might be affected. It'll just be a streak through the one thing. So our software is smart enough not to sort of track on the 1 out of the 4, streaks in those images. So we're really not affected by that, fortunately. But sadly, I know other astronomers are affected by that constellation, and as you guys know, there's more of those constellations to be launched. There's probably going to be tens of thousands, maybe hundreds of thousands of those things flying up there, unless there's better regulation or mitigation of their reflective properties. We'll see.
And how many? And this is again from the audience. How many comets have been discovered by the project, by the survey?
Hundreds. Yeah. I'll get into that a little bit later. We sort of serendipitously, bump into new comet candidates. And if they're not identified as a comet by the observer, maybe it just looks asteroidal, it doesn't have any coma yet, then they just get the name of the project. It's either a comet Catalina or a comet Lemon if it's discovered from the telescope at the summit. However, if the observer discovers it in those initial images, hey, this has a coma, it's got a tail, I'm describing it well enough, I'm going to report it as a new comet candidate, then fortunately on our project, those comets bear our surnames, which is really a nice fringe benefit to finding near-Earth asteroids. So let me zoom in on this flat part of the curve here, a little time throwback here. I started near-Earth asteroid surveying at Mount Palomar in 1992 with Gene and Carolyn Shoemaker, and David Levy, of course, was observing with them. And during one of the runs, they discovered Shoemaker-Levy 9. Unfortunately, I was not on that run. And frankly, it probably wouldn't have been me that discovered anyway, because David Levy had the presence of mind to say, hey, it's a cloudy night. Let's observe anyway between clouds. Let's use some old films. What the heck? And they looked up by Jupiter and found the comet that is now, famous. But anyway, this was the film-based days, working in dark rooms and wet chemistry. The pipeline to discover a near-Earth asteroid was days or weeks. Maybe we'd take films back to Flagstaff, and I'd work at Lowell Observatory on doing the astrometry and taking the measurements of the star fields and finding the positions of the asteroids. So, going from sort of a discovery pipeline that's days, maybe hours at best, to days or weeks, to literally, seconds and minutes here with Catalina. It's pretty cool to be part of that span of history.
Another question. Have you encountered any objects with nonlinear motion?
Yeah, for sure. The impactors, they are quickly flagged. I should mention there's another NASA project called Scout, and that's based at JPL, Caltech. And every object that we discover, that astrometry, those positions get sent directly to them. And they do a deeper computational dive on those positions, even the initial positions, which only represent, 20 minutes of an orbital arc that might go a long ways. So if an object is approaching Earth, it's going to be curved by Earth's gravity well. And projects like Scout identify that nonlinear motion rapidly, and they say, hey, this is an object that we need some, rapid follow-up on because, it might be in near Earth space. We need to get more positions to see if it's an impactor, and otherwise, certainly to keep tracking the object. So yeah, we do get objects that have nonlinear motion. All right, well, here's a transition now to, we talked about the lousy effects maybe of near-Earth asteroid impacts and some of the good effects. And Gene Shoemaker probably said it best that, impacts, asteroid and comet impacts are the most widespread geologic process in the solar system, certainly on the terrestrial planets. It's really how they were formed. If you think about the accretion of planets from what I'll call sort of soft, gravitational impacts to, larger, more violent impacts. And of course, the transformation of landscapes in the entire planet as they might be affected by large impacts all through their history. So the world's water, as it turns out, is largely, originated in asteroids. It used to be believed that the world's water came from comets. Comets are icy bodies, they're volatile, they carry a lot of water. It's not a stretch of the imagination to think that a high flux of comets early on in the formation of the solar system, it produced a lot of water on Earth. However, looking at the stable isotopes of comets and asteroids, we see that there's a very close match with carbonaceous chondrites. So most of the world's water likely originated from chondritic, impacting chondritic asteroids early on in the solar system. Organic compounds as well. The Earth may have had, or it may have developed, complex organic compounds, including amino acids, the stuff that life itself is made of and dependent upon. But if Earth did not have, these complex molecules, they were certainly then delivered, or at least, augmented by the impact of carbonaceous chondrites.
Is that your computer, Mr. Leonard, making that noise, that chiming?
Yeah, let me see if I can kill that.
Oh no, I just wanted to verify it was yours and not extraneous someone watching.
It's my Slack. The guys at the summit, he's communicating. We communicate that way across mountaintops.
Okay.
I'll attend to that in a bit, but I apologize for that.
No, as long as it's coming from your end, it's okay.
Yeah. So how do we know all this? Well, meteorites, are often called sort of a poor man's space probe. And one gentleman earlier here said he's an earth scientist. Well, I am a geologist by training. I kind of come from the Gene Shoemaker School of Planetary Science, and I studied geology and got into planetary science that way. Now, in geology, when you're out mapping on the Earth's surface, a lot of times you don't have good outcrops, and so you just see a lot of boulders and cobbles on the ground, and that stuff came from eroded, outcrops somewhere upslope or somewhere upstream. So you use that as a guide, as information for what you might encounter as you walk upslope or upstream. Well, the same thing with meteorites. These are probes from their parent bodies, which are the asteroids, including the near-Earth asteroid population. So in studying, meteorites, we have a good idea what the asteroids themselves are composed of. And that's why we have a good sense of, what goodies reside within these things. So, what do asteroids have in them that we have interest in? Well, carbonaceous chondrites, they can contain up to 22% water. And a lot of that water is bound up in hydrosulfates, phytosilicates. It's not, ice. It's not volatile water, but it's the kind of water that's easily broken out of those molecular bonds. Of course, the iron nickel asteroids, they are pure high-grade stainless steel, iron, nickel, cobalt. Plus, they're rife with precious and strategic metals, gold, platinum, osmium, rhenium, iridium. And then finally, the ordinary chondrites, they contain lots of water and also the free metals as well. So why do we care? Well, near-Earth asteroids, let me try to kill that. That is really good. I'm trying to find the the application here, but I don't want to kill the, I guess I'll have to let that continue. Apologies for that, folks. So near-Earth asteroids have resources like the water, which will be used as rocket fuel, human consumption, of course, the base metals for manufacturing rockets, housings and structures, precious metals, which will be used as catalysts to construct all the above, and semiconductors, which we'll use to make, solar cells. So make no mistake, near-Earth asteroids are our ticket to our future in near-Earth space and our exploration of space. Okay, this is for, I guess, at least the one geologist out there in the crowd, and this is sort of a call out to asteroids in general. So this model here, quite simply, is pretty much a model of a differentiated planet like Earth or a very large asteroid. So when bodies get this large, they will separate out, the denser chemicals and elements. So everything is sequestered in the core. 99% of the iron, nickel, plus all these goodies here, these precious and strategic metals, are sequestered in the core. So we live out here on this thin rind out here in the crust, and you might think that the Earth is just abundant in elements and metals that we need, because we see cars and houses and airplanes and all this. But as an exploration geologist, I used to go out looking for these things, copper and gold and platinoids. This stuff is rare, folks. It's really hard to find, and it's only where Mother Nature, volcanically, tectonically concentrates and focuses these things in the thin crust do we find these. If you were, say, an alien civilization that's moving from star system to star system, and then moving into our solar system, and you needed more materials to build your armada to continue expansion, the last place you would go to for materials is a planet like Earth or a large asteroid. Where you would go would be over to the ordinary chondrites and the carbonaceous chondrites, because these are undifferentiated bodies. These have all these goodies, but they haven't yet been differentiated. So they have a homogeneous abundance. These are essentially floating ore bodies. Okay, so this is one reason why asteroids and near-Earth asteroids are the place to go and find the materials that we need to explore space. There is one exception, okay? If you have this differentiated body like a medium to large asteroid, it's got all these goodies in the core, and you smash into it, it's going to make all these fragments. And we know that there's pure iron nickel asteroids out there, and that would be these blue ones here that have been exposed after the impact, and eventually they make their way into Earth crossing orbits. And remember that a near-Earth asteroid, by definition, these are asteroids that come to us, and that makes a big difference. That makes a big difference because near-Earth asteroids are actually energetically less costly to get to than our own moon. Now, I sure hope we go to the moon and have colonies and settlements and exploit all the elements and the water that's available on the moon. However, for broader exploration plans, it's really the near-Earth asteroids. And this illustration shows the delta V, which is simply the change in velocity required to access these bodies, to land on them, and to escape their gravities. And you can see there are thousands of near-Earth asteroids that have a lower energy requirement to get to than our very own moon. That makes a big difference because we can carry more payload. The cost of the missions are less. So near-Earth asteroids are, again, our ticket to space exploration. That said, it's not a one-size-fits-all. Just because it might take less money and energy to get to it, there's a lot of conditions and circumstances that make any given near-Earth asteroid maybe difficult to access at any given moment, where it is in its orbit, what is its return cadence? Is it 1 year? Is it 2.5 years? There's a lot of factors. There's actually a couple companies that have been started. One of the companies I think has kind of been bought out, Planetary Resources, and then there's Deep Space Industries. But these are companies that are looking to exploit near-Earth asteroids, and they kind of had, I think, kind of an aborted start. They started a dozen or more years ago, and I guess they didn't attract quite enough investment. They might not be quite ready for prime time. But people are really dreaming about this stuff, and there's a lot of folks working on how to access and how to mine and how to process and use these materials. But again, there's some really serious conditions that need to be overcome: the hard vacuum, microgravity, radiation, extreme temperatures, and these sort of things. Okay, kind of to wind up here with a few slides. I touched on this a little bit earlier, that in the process of discovering, lots of near-Earth asteroids, we also discover other things. We discover thousands, and this is an understatement. This is probably more like hundreds of thousands of main belt asteroids. On a long winter night, if I'm surveying along the ecliptic or near opposition, I know that I have posted at the end of the night. We don't submit these things as we discover them, because main belt asteroids are not of interest to us. They're just garden variety, they're inconsequential, but they get submitted, their positions, at the end of the night. And I know that I've submitted upwards to 1,500 maybe, or 2,000 new main belt asteroids in a long winter night. Mini moons, 2006, the first temporarily captured asteroid was discovered, and just last year 2020 CD3 was another temporarily captured mini moon. It was only a few meters across, but it's an object that sort of was in Earth orbit. It was essentially a second moon temporarily before it got flung back out into its heliocentric orbit. It will return to Earth, maybe to be recaptured, or maybe eventually to be flung further out into space. Trans-Neptunian objects, we don't get many of these, but now and again we do pick up these really distant, Kuiper belt scattered disk objects. We picked up impacting space junk. There was an object that impacted over the Indian Ocean about 5 years ago that we found. I actually picked up Elon Musk Tesla when that was launched. I think it was a couple of years ago, and tracked that for early one evening. That was a lot of fun. And as we mentioned, hundreds of comets have been discovered here, which is a whole lot of fun to discover comets. I've discovered 12 comets now, including 3 this year alone. And I'm going to talk about the first comet I discovered this year, which was C2021A1 Leonard. And this is an object that some of you have probably heard about. Shortly after its discovery on January 3rd, it was quickly determined to be an interesting comet that was going to have a relatively close perihelion of about 0.6 astronomical units, and relatively close Earth approach of about 0.2 astronomical units. And this is all going to occur in 2 months from now, in December and January. So this object, this is actually the discovery images. This is what the preliminary designation was, our CSS designation. This is what it looked like to me on that early morning in January. And some of you might be able to detect just a little bit of a coma and a tiny bit of a tail sort of pointing off here to the right. That's what I saw. And this is fairly typical of, our new comet discoveries. This was about 19 or magnitude 19.5 magnitude. So we're seeing some really dim stuff. This is almost 1 million times dimmer than what we can see with our naked eye. So that's what it looked like. It's incoming. The brightness curve was pretty flat over the summer, but now the object has picked up in activity since late August and early September. This is an image that was taken by Michael Yager just 5 days ago. So you can see the comet is showing a nice dusty tail. And it's currently at a roughly magnitude 13, 14-ish. there's some hopes that it might get as bright as magnitude 10 by the end of this month or early November. Here's the brightness curve since its discovery in January right here. And you can see all these points here. It's sort of flattened out, unfortunately, in the summer, but recent CCD observations have it picking up in its brightness rather quickly. The gray line represents the initial modeling of its brightness curve into December, January. The red curve is sort of the real-time modeling based on the most recent observations showing here. And the green shows the potential for forward scattering. It's a comet that will have sort of a high phase angle, and it's going to be roughly between us and the sun. And the idea is that the sun is going to enhance all the dust particles, and it may boost the magnitude by 1, 2, and in some cases up to three visual magnitudes. We'll wait and see. This is an orbital diagram. They're always a little hard to see statically. There's some online tools through KPL, the small body database. Get on there and plug in this object or any object, and you can kind of play around with animations. But this is where the object is now, October 15th. It's coming in from the northern part of the sky. It's a circumpolar comet. And well, let me click to the next one. This is December 9th, and here's Earth, the comet. It's going to be an object that is first and maybe best visible in the morning sky, and then eventually going to shift to the evening sky. And interestingly, this object, even though it's a long period comet, it comes close to clobbering Venus. It's going to go right across the orbit of Venus, and 3 days later, Venus goes through, part of where the tail had just gone through. And there is some speculation that Venus may undergo a meteor shower. And so that's something that we hope that the Japanese spacecraft, Akatsuki, that's orbiting Venus, might have a chance of seeing some of those meteors. Sky and Telescope just came out with some of these maps. I think it was published yesterday or today. And this shows the early December sky where the comet's going to be December 3rd, relative to Arcturus and Bootes and the 6th, and then getting lower and lower as you get into mid-December. And then it's going to shift into the southwest sky at evening time. It's going to really skirt across the horizon in the southwest. It'll be a really challenging object to observe at that time, but it's going to be close approach to Earth at that time. And with the forward scattering, I think it's going to be worth really trying to get out there and see it. All assuming that it doesn't disintegrate before it even gets there, which as many of you have tried to observe comets, incoming comets, that can certainly happen. Think of ISON and Kohoutek 1973. So, is it going to be fair, good, great? Nobody knows. I guess I didn't put the word dud. That's always a possibility too, if it breaks up between now and December. This is an image I took atop the Santa Catalinas of Comet Neowise last year. It was a beautiful comet, kind of surprised all of us. And I think David Levy, said it best when he said, comets are like cats, both have tails and both do precisely what they want. So it's wait and see for Comet Leonard, but we're all certainly hoping for the best apparition. Thank you for your time tonight, listening in. I'll be happy to stick around and entertain, any questions that y'all have.
Thank you very much, Mr. Leonard. Thank you very much.
I have a question. How faint of a magnitude do you pick up on your 30-second exposures?
Yeah, it's kind of a function of the telescope. I'll talk about our 60-inch telescope at the summit of Mount Lemmon. On a good night of really stable seeing, we can get down to V22, even V22.5, more nominally 21.5, 21.8, but really dim stuff.
And in case you haven't noticed, Greg, if you look at over my shoulder, that's one of the comet Catalinas as my background.
Yeah,
I
awesome.
need to
Yeah, there's been
look
some
up
good.
which one it is.
Comet Johnson several years ago was a notable Catalina discovery as well. But this is probably the brightest one that we've discovered, to date.
I have a question. How can we be sure that DART won't deflect the object toward the Earth, or for that matter, that approach in general to perhaps more hazardous asteroids?
Yeah, that's a great question. I think that I'm hoping, I don't know the answer, I'm not on that project, but I'm hoping that the engineers have really thought about that very well. I believe it'd be my speculation that the projectile, the impactor, is small enough and it's going to have a velocity that's only going to maybe change its orbit. It's likely going to stay orbiting or co-orbiting along with the primary asteroid Didymos, and it's probably not enough force to send it careening off into a whole new orbit. But again, I'm not part of that project, so I don't know. And humans have certainly bungled things in the past. So
yeah, that's a little worrisome. I've been asked that question myself by people that have heard about this project, but let's hope they have it right.
Let's hope they have it right. Yeah, exactly.
And another question from our audience is, do you have any thoughts on Planet 9 or Planet X, as they call it? The supposed planet that's supposedly out there?
Yeah, I mean, I'm intrigued like everybody. I've been following, it's sort of been, back and forth between, the proponents that it must exist. It has to be out there. And here's the place that it should be, to those that are like, no, it doesn't have to be there. Or it's not there. So I don't know. I'm just kind of following along our systems, our cadences of our coverage, and the depth at which we can sort of see the night sky. We'll never probably discover, a Planet 9 here. Those are likely require much larger instruments to be looking for it. But I'm intrigued. I'm all for it. Apparently, if there is a Planet 9, it's a super, super distant object, and it's actually, pretty darn big, almost like Earth or sub-Earth sized. And you would think, how can something like that hide out there? But, space is really, really big, and it's a needle in a haystack kind of search. So like you, I'm just staying tuned to what's going on.
Wasn't it just last year, late last year, that there was a discovery by an amateur astronomer of a 1 kilometer asteroid?
It's hard to keep up with all the discoveries. 1 kilometer, I'm not sure about that. Yeah. Send it on to me if that's the case. Maybe it was a near-Earth asteroid. That would be quite a unique discovery. But amateurs are, really punching above their weight more and more every year with, instrumentation, sensors, processing speeds, and just flat out, ingenuity and capabilities. So I love it. I love seeing that. And if they can outcompete us even for a night, I'm all for it. Any other questions? Can't really see the chat. So Raj,
Yeah, as long as you're screen sharing, you can't see the chat. But I've been posing questions from the chat as they come up. Okay. And I'd like to thank you again. This was an outstanding presentation, very informative, very interesting.
it was my pleasure, and I sure hope after the COVID era that I'll feel more free to travel, and I'd love to go and see your facilities. It looks like You're an extremely active and exceptionally talented group, and I just love to see what you have going there. And also, if you're ever in this neck of the woods, you know, once it's safe to come out and play, you know, I'd love to meet up with some of you folks, and you know, maybe you can come up and see some of the telescopes up here too. But it's been a pleasure tonight to share some time with all of you.
It would be wonderful. I haven't been to Tucson since the late 80s. I need to get back.
Yep.
All right. Well then, thank you very much for your time, sir.
I stopped and share there, so now you're free.
All right. Are there any other questions for our distinguished speaker?
Well, I've got one question about a specific asteroid. I mean, even though it's estimated at only 13 meters in diameter, is there any talk about targeted observations to try and recover risk-listed asteroid 2009 JF1 around May 2022? I don't know if you guys have even spoken about that one, or if NASA has sent anything out about that for, you know, any targeted observations or not.
Yeah. If anything is like on the century list, once the observing circumstances are suitable for us, you know, these objects come up immediately for us to look for, not only us, but, you know, other facilities. In some cases, it might be too dim for us to pick up. So other more capable, larger instruments, you know, would be searching for that object. But if it's a virtual impactor, yeah, these are objects of high interest, regardless of, you know, whether it's 13 meters or smaller. So I don't know the specifics of that. I'm going to look it up and see, you know, what the estimated visual magnitudes will be.
Yeah, the nominal orbit only has it at about magnitude 24. So you guys would have to take, you know, if it was a targeted observation, I assume you guys would have to take a 3-minute shot of it to have a shot at it. And
yeah, it's something that we could do, and also with the 90-inch on Kitt Peak, you know, it's something we might go for. And otherwise, for sure, there's going to be other large, you know, instruments, you know, around the world, you know, looking for the object. There's no doubt.
All right then. Well, thank you. And it is almost 9:30 p.m. And I'm sure Mr. Leonard needs to attend to his work. But this has been a fascinating presentation. This was thank you so much for taking the time and the effort to speak to us. We would love to have you, if you're ever in Sacramento, we would love to have you pay a visit to our observatory or meet up with us in person. You know how to reach me, although I'm probably the person you least want to speak to. But definitely we would love to have you out here when travel and in-person meetings become free again. And again, thank you for a wonderful, wonderful presentation.
Thank you, guys.
Thank you so much.
thank you.
Really good. Enjoyed that.
You folks have a great evening, and enjoy your weekend as well.
You too.
All right. With that,